So in our prior lectures, we discussed the energetics of why reactions proceed, or at least how they proceed energetically. That didn't probably wasn't extraordinarily satisfying in that you really didn't see any new molecules being made. But in order for a new molecule to be made, I guess we have to really talk about real molecules. And we had discussed this concept in the past. This idea that you have a molecule that has a lone pair. We called it a nucleophile, right? And it had a lone pair, and it's a nucleophile, and I refer to it as a nucleophile because it loves nuclei, all right? And it loves nuclei in the sense that it loves positively charged stuff. So nucleophiles attach things that have a strong positive charge, and if you want to give a carbon a strong positive charge, you have to attach it to something that has a pretty good electronegativity. And chloride is one of those atoms. And so this is a great example of a highly polarized molecule that imparts a pretty substantial partial positive charge of the carbon, because we can draw, in fact, let me just draw the three-dimensionality of this a little bit more clearly. As we have a hydrogen here, and that gives us this dipole that goes up this sigma bond here. And if I were to draw, how the electron distribution around this would look, it would be more like that, where most of the electrons are actually hanging out up at the chloride, given this carbon what we call a partial positive charge. That means that nucleophile, which loves nuclei, sees a nucleus here, because the carbon electrons, they're not very evenly shared. And so those electrons go and they attack right at that carbon. In fact, they specifically attack at the antibonding orbital. So this back lobe that I had discussed in the early lectures of hybridization, that will allow for the substitution of the chloride with the approaching nucleophile. Okay, so this reaction is something that's going to only happen on something with a good, strong dipole. It's not going to happen on, say, ethane. See, so if I were to write this out generically, I would have a nucleophile, okay, and that would have a lone pair. It could also have a negative charge, and it would attack something with a carbon halogen bond, for instance, or at least something that will leave. And we'll call it a leaving group, so we'll call this a leaving group. And as a consequence, what you see is a substitution of that halide or leaving group with the nucleophile. All right, and this is called a substitution nucleophilic reaction. Well, it's abbreviated Sn. All right, and there are a couple of different ways this reaction can happen. If the nucleophile attacks the carbon and the X leaves, and this all happens at the same time, it's called an Sn2 reaction. If the X leaves first, making the carbon positively charged, and the nucleophile attacks it, that's called an Sn1 reaction. And I'm going to clear that up in just a minute. But to be clear, there are a couple different case scenarios that dictate what kind of substitution reaction you end up with, and that's really what the meat of this lecture is going to be about. Now, before we get into the very specifics, let's really cover what nucleophiles are, because we're really going to have to talk about nucleophiles a lot. And we say nucleophiles, and we mean either charged substrates, so hydroxyl groups, ethoxy groups, well, that's a methoxy group, methoxy groups, ethoxy groups. Often I drew in the early days, and just like I drew up there, neutral molecules that have a lone pair of electrons, like amines. Those are really good nucleophiles. Things that have a lone pair that it doesn't mind donating. Amines don't really mind becoming positively charged per se. You can buy lots of stable ammonium salts, for instance, ammonium chloride, all that kind of jazz. Perfectly stable, you can put it in a bottle, because those lone pairs are pretty reactive on the amine. Negatively charged ions tend to be really great. So you don't really see a lot of the super electronegative atoms. F minus, okay, while it's charged, true, and it has a negative charge associated with it. Fluoride jealously guards those negative charges. So does chloride, as a matter of fact. It's really actually not very good at being a nucleophile. It's just too electronegative. But as you go down the halides, you start to get less electronegative, and you actually find that bromide is not the best, but iodide then actually becomes a reasonably good nucleophile. And you start to see that these are good over here, and these are bad, and then they kind of go over here to actually being, let's say, good nucleophiles, okay? And this has a lot to do with electronegativity. Not exclusively. It's a bit more complicated, but you can rightly imagine that fluoride being super electronegative means that it's actually so electronegative it's not interested in giving up its electrons for a nucleophilic attack. Iodine is less so, and it's more capable of giving up its electrons. In fact, it really wants to give up its electrons, and it's quite happy to be a nucleophile. Oddly enough, it's also really good at being in a leaving group. Again, something we'll cover in just a bit. But nucleophiles, generally electron-rich, really eager to give up their electrons and form a new carbon bond. Conversely, the things that these attacks, things that nucleophiles attack, are called electrophiles. All right. And let's just move this over here so that we can get a good compare and contrasty kind of thing going on. Electrophiles, on the other hand, they are partially positive or positively charged species. You find, carbocations, and we said that carbocations that are tertiary are stabilized. Well, they're stabilized. They exist. Carbocations are reasonably good. Things with really big dipoles, or things just with reasonably large dipoles, are actually pretty good. So I drew up there your prototypical example of a good electrophile, and that is this really polarized carbon-bromine substrate. And that makes the carbon more of an electrophile. And to be clear, the electrophilic aspect of these is the carbon on both of these. They are the ones, in this particular case, they just have an outright positive charge, or in this case, they have a sufficiently large partial positive charge that makes them attractive to negatively charged groups. Now, I had alluded to this idea of an Sn2 type reaction. All right, so an Sn2 is a substitution nucleophilic type 2 reaction. All right, and type 2 means it's bimolecular. So this is a bimolecular reaction, which is, kind of funny, because if you're going to have a chemical reaction, shouldn't they all be bimolecular? I mean, there are some reactions where just one molecule decomposes, but you look up here, and I've sort of not given you much wiggle room in the substitution nucleophilic. How are you going to have a substitution with one compound for another if it's not going to be bimolecular? And this is where kinetics comes in. So the kinetics and all the stuff we discussed in the last lecture really starts to gel in this particular reaction sequence, okay? Because in an Sn2 type reaction, we have a very specific energetic landscape that occurs, all right? You have a nucleophile, all right, and you have some carbon with a leaving group. And that's got 3 substituents coming off of it, and that has some sort of energetics. And it's going to have to go through some unisolatable, improbable looking transition state to finally get to something of a lower energy. And that's the substituted product, so that's going to have to be the one with a nucleophile, and you've got the carbon, and now the leaving group is somewhere over here, right? So what is this high energy complex all the way up there? What is the as we defined it in the previous lecture, the transition state. And all Sn2 reactions have this energetic landscape. They all go through a 5-coordinate, so a pentacarbon reaction species, where you have the nucleophile approaching. So the nucleophile is like bound to the carbon, and this is a 5-membered carbon. And as I said, 5-membered carbons don't really exist. But I also said transition states, they're unisolatable hypotheticals. Now, in order for this reaction to exist, you have to have a bond formation and a bond cleavage that occurs at the same time. And that is what this is. The idea that you have this leaving group, this L, is coming off. That bond is breaking while this nucleophilic bond is forming. That is the idea behind an Sn2 chemical reaction. So, to put it into a more realistic looking example, a pretty frequently or pretty well known nucleophilic reaction that undergoes Sn2 is going to be something with a really strong small nucleophile like hydroxyl groups, and something with a really polarized bond like an alkyl halide. All right, and then you have methyl iodide. And what you have is the electrons, and we draw our arrows in the flow of the electrons always and at all times. They flow in the direction of electrons. Physicists have gotten this wrong forever. For some reason, they do it the opposite way. I don't know why, but physicists are wrong. And what we see is that the electron, or the transition state structure, is this wonky 5-coordinate carbon transition state, and you end up with something that looks like that. I'll just write out transition state, even though that's a fairly long looking word, and I've not given myself enough space to really do my beautiful artwork justice. And then you end up with your final product, the hydroxyl group on the other side of the methane. So now you've made methanol. And of course you've added to the mix an I-. And you'll notice that there's something interesting I want to point out. It's not interesting, you should expect it. The two starting materials have a negative charge and a neutral charge, so that's a -1 overall, and the final products have a negative charge and a neutral charge, so a -1 overall. And that reaction, if we were going to draw the kinetics of this reaction, we wanted to know the rate, and this is what makes an Sn2 reaction. The rate of this reaction is defined by some K, some constant, and the concentration of methyl iodide and the concentration of hydroxide. And we know this because there's no way to make this transition state without both of these compounds being present at the exact same time. So now I presented that in the exact opposite order it was actually discovered. First, people realized that the rate was dependent on the concentration of both starting materials. That then allowed them to infer that the transition state must be a combination of both reactive species. All right, and that is how kinetics, or experimental detail, helped allow us to understand the theoretical aspects of these reactions. That was an important connection that we were able to make with determining how these processes work, was that we used rate data to identify the mechanistic intermediate transition state that's associated with it. All right. Now, a second consideration for Sn2 reactions is, you notice in this geometry, you end up attacking from the opposite side of the leaving group. This is a process called backside attack, and it has an important implication in stereochemistry, in that the leaving group is always 180 degrees away from the nucleophile, and that means that you will end up with an inversion of stereochemistry. So if we were going to take something like, say, substrate where you have a CH3 here, a carbon, a chloride, and that is going to be a CH2, CH3, and then in the back it's going to be an H, right? And then we're going to have a really strong nucleophile like phosphine. Phosphine is going to come in, and I'll explain in a bit why that's a really great nucleophile, but it's going to attack on the opposite side of your carbon. Now, it doesn't make any difference if we were going to number these. Chlorine is 1, ethyl group is 2, methyl group is 3, and those are in the back. 1 to 2 to 3 to 1. That is a clockwise rotation. Let's move this over here. Now, if you look at the transition state structure of this, you have a 5-coordinate carbon. It's coming in. Chloride is leaving. CH3, it's a trigonal bipyramidal structure where the ethyl group is popping out towards you, and then the hydrogen is going away from you, and you get the final outcome with the chloride being gone. Now you have a phosphine coming over here, and it's connected to a carbon, and now the CH3 is over here. Still have the ethyl group coming out at you, and then the hydrogen is in the back. But now look at what happens to your stereochemistry. Phosphine is still the largest one, so that's still the biggest, and that's 2, and then that's 3. But that now makes it go in the opposite direction. All right, and then that gives it an S. So another consequence of this Sn2 chemistry is an inversion of stereochemistry in this reactive process. This reaction is facilitated. It's got an associated rate, all right? And we had discussed, because we're in kinetics, we might as well look at the associated energy of activation, which is this thing right here, remember? The kinetics, they're the kinetic component, and the energy of activation. And that's in my generic sample, so this is just generic nucleophile. I have drawn a, I don't know, this is totally relative. Who knows if that energy of activation is high or low? But what I can tell you is that the energy of activation scales with the power of this nucleophile and with the power of this electrophile. And what do I mean by that? The more nucleophilic this is, the lower the energy of activation is. And the more electrophilic this is, the lower this energy of activation becomes. So what then, as I've described up here, or the relative magnitudes, the relative powers of these nucleophiles? I kind of went over here. In fact, I explicitly went over here saying that iodide is a really good nucleophile, which means that it would have a modestly high energy of activation, whereas fluoride is a bad nucleophile. Okay, not that it is impossible, but the energy of activation would be enormous, and you would have something that would look like that. The reaction diagram essentially states that you would have to heat the reaction up to infinity in order for you to actually achieve product, which you would get decomposition and probably fires if you tried to push a fluoride to be a nucleophile. So in that way, we can control the speed of the reaction with our nucleophile. Of course, to be clear, it's a substitution reaction. So we are taking one of these, we're taking iodide, for instance, and we're sticking it on to make a new product. So that's going to change our relative energetics down here as well. So let's, as an example, say I have a reaction coordinate here, and I'm going to propose 2 different reactions. We're going to keep my electrophile the same for reasons that I'll get into a bit. This is actually a really great electrophile. iodide is one of those weird atoms that, in addition to being a really great nucleophile, also is quite okay just also popping off of a molecule. Iodide is very strange. And let's say, for instance, we have two different possibilities. Let me do a reaction, and we're going to do it with, say, either water. All right, and water's got lone pairs. It's a nucleophile. Or we're going to do it with hydroxide. All right, and hydroxide has got a negative charge, so it's going to be a much better nucleophile. And you can probably assume why. And what you'll end up with then, depending on which one you go, either let's say we go with the hydroxide. What we will then do is we'll go through some interaction that will lead us. So this is our hydroxyl group. We're going to have to draw a transition state here. And let's see here. What does that transition state do you suppose it would look like? Hopefully you can do this in your head with me. That's going to be a carbon, and it's going to have, in fact, let's switch this to white so that I can be quite clear. We're going to have a carbon, and that's going to have an iodine, and then that's still going to have a hydrogen, and hydrogen here. But on the other side, it's going to be an OH. All right? So that is going to be our transition state for that particular reaction. And then the final product down here is going to be H3 bonded to OH. All right. Now, on the other hand, if we went the route with water, we already said that the water is going to be not as good of a nucleophile. So it's going to require a bit more oomph to get over there, which is convenient because I need to get over that transition state structure I just drew. Now let's draw the transition state that I've just created. Now, our transition state, our pentavalent carbon is still going to be pentavalent. That hasn't changed anything. This is still ostensibly an Sn2 reaction, so we can draw it like that. We can draw it like that. But now let's draw water off of this. Okay, so now we're going to draw water, OH here. Okay, nice. But I've drawn 3 bonds to oxygen. Okay, and 3 bonds to oxygen means that that's going to have a positive charge associated with it. And that's fine. That's okay. All right. But we are going to have to keep track of it because that's an important aspect of the reaction. And that's our transition state here. I'm going to move this whole thing up out of the way. And we will continue our descent down to product. The product in this particular case is actually less stable because it's positively charged, right? So as the transition state moves on, the iodine does ultimately come off. You do end up with CH3, except you end up with this OH plus, okay? So you're going to either need a base to come along and pull that hydrogen off, because that's going to be a very acidic proton. But if no base is available to come off, it will just climb right back over and go over here. You can see that I have drawn it so that there's very little energetic difference between this product and the starting material. And with water in particular, it is true that the reactions tend to have a large equilibrium. They flip-flop back and forth, in addition to being slow to begin with. Whereas the hydroxyl group, you immediately proceed to a fairly stable reaction, which means your equilibrium will strongly favor product formation, and the reaction is going to be much faster to begin with. So those are reasonably good predictors of your reactivity. And just as an aside, if you were wondering, yes, you generate I-, and over here you generate I-, and I- can come along and deprotonate that in another reaction that will give you this final product. So you'll make HI, which is a very strong acid, and that H can go back onto the oxygen and it can kick it back. So at the end of the day, the best way to proceed with this whole process is just to use the stronger nucleophile. That gives you a more stable final product, or at least a more stable intermediate product, and it is faster. Now, I have specifically said that the electronegativity is an important part of nucleophilicity. And I did just say that iodine could have acted like a base. And so the question is, why? I mean, let's be quite clear. You could also say that these are bases. That's a base. That's a base. We've shown that that's a base. And I've actually kind of drawn this in the form of conjugate bases, right? So this is actually a terrible conjugate base because it's an awesome acid. HI, hydroiodic acid, really great. HF, I've said, is a very bad nucleophile, but it's actually a bit more basic. So what is that relationship between nucleophilicity and basicity? So in the context of nucleophiles versus bases, you're still trying to really profile what the difference is, or what really makes a good nucleophile. And we know what makes a good base, because we went over acids and bases. A good base, at least a good Bronsted base, is just something that can pull a proton off. And you've got a negative charge, or you got a lone pair, and it's going to pull off that proton. It's going to kick those electrons that originally formed that thing over onto the leaving group, or the conjugate base. The conjugate acid. And you're going to end up with a new conjugate acid and a departing anion. All right, and in a periodic table, strictly speaking, this is 100% related to electrophilicity. All right, the more electronegative a compound is, the better base it is. That is not true for nucleophiles. So bases strongly follow electronegativity. Nucleophiles do not, all right? Nucleophiles actually do not strongly follow electronegativity. They follow something a little bit more complicated than electronegativity. They follow the softness of the atom in question. The softer an atom is, the more nucleophilic it is. Of course, it's really got to be able to like electrons, but it has to be a bit soft. And what do I mean by soft? So if we were to look at the periodic table, let's just draw a periodic table here. Right, and we associate the electronegativity. It's going to go like that. All right, that's his electronegativity. And this is electronegativity. Okay, and your little atom, fluorine, chlorine, bromine, iodine, those are going to be, the fluorine's going to be by far your most electronegative right here. On the other hand, softness is related to size. The bigger and the fatter an atom is, the softer it is. Okay? So in that case, if we were going to draw softness, we would actually start going this way. So in addition to being more electronegative, iodine is actually softer, and bromine is softer, and chlorine is harder, and fluoride is very hard. And what does softness have to do with nucleophilicity? Great question. Let's go back to the atom. The atom has neutrons. I don't remember what color neutrons were. Neutrons were white, that's right. You had neutrons, and then you had protons. Okay, and the protons were the positively charged business. And then around those you had electrons. And as this structure became larger and larger, as you go out down in the periodic table, what ends up happening is you start to add more neutrons and of course more protons. And the nucleus really starts to get, pretty big. And that means also that the electrons have to space out with their orbits. The orbits start to actually get pretty far away from the nucleus because, you've got to start spacing them out. So that's your first shell. Then you got another shell out here. Then you got a shell out here. And then you're starting to throw electrons all the way out here. And the electrons, as they move further and further away from the nucleus, actually feel the pull of the nucleus a lot less. And so what happens when a atom of similar disposition, shall we say, another rotund atom comes within close proximity, is that they can actually attract each other because these electrons, by virtue of being far enough away from the nucleus, don't mind being repelled away from each other. So these electrons actually can end up navigating themselves away down here to the opposite side. And that means that these things, so there's a partial charge, I guess I should actually illustrate this partial charge. There's actually a partial charge closer to this side and a partial negative charge on that side. And likewise, just on this side and this side, you have a dipole developing in these soft atoms, and these soft atoms can then rotate around and they can start interacting with each other. Lo and behold, two soft atoms can start interacting together. So as it turns out, soft atoms, they like other soft atoms. And that's okay. They have found their role, they know who they are, they like what they like, and they should be accepted for that. And we do. Soft atoms like soft atoms. On the other hand, when we're talking about bases, all right, bases like protons. And a proton is about as hard as you can possibly get. A hydrogen proton, the H+, has no electrons. It is incapable of this polarization here of a soft atom, which means that a proton is infinitely hard. And so a good base will also be really hard. It will not polarize, which is why good bases tend to be these smaller, more compact atoms. Bases, and they just go after a positive charge. They see the harder it is, the more they attack it. So hard bodies like hard bodies, and soft bodies like soft bodies. And where is carbon on all of this? Somewhere around here. So carbon is not hard like hydrogen, which is all the way over here. And it's actually a bit softer than hydrogen, which means that nucleophiles, the better nucleophiles, tend to be a bit softer than the bases, right? So bases like to attack hard things. Nucleophiles, they tend to prefer to attack soft things. And how do we know that this carbon is quite soft? Is it polarizable? Yes, it's quite polarizable. So nucleophiles are really, actually, they just love soft things. They love soft, squishy, polarizable things. And in general, as I've drawn it here, yeah, a good base is probably going to be a pretty decent nucleophile because they both have this electronegativity concept together. All right? But they also have, nucleophiles have this second parameter. They like soft bodies. They like squishiness. So let's draw out the additional atoms in the periodic table. So we've got carbon and not sulfur. All right, let's fix that. All right, you have carbon, and then underneath that carbon you got a silicon, then nitrogen, and underneath that nitrogen you've got a phosphorus, and then next to nitrogen you've got oxygen, underneath that oxygen is not silicon, gas and Smith, sulfur. All right. Now, this trend is going to be bearing itself, so let's just say, which is the better base? NH3 or H3P? All right. Well, based on this analysis up here, ammonia is going to be the better base, and phosphine is going to be the better nucleophile. How do we know this? If we take the conjugate base, we take the conjugate acid of both of these, this is several orders of magnitude more acidic than this. So by that context, this is by far the worst base. On the other hand, if we were to throw these both into a reaction with this compound, the phosphine, would react orders of magnitude faster than this one. So it generally holds that these compounds, these bigger squishy compounds, phosphorus and sulfur, while they are not as good at being bases, they do make slightly better acids when they're protonated, and they're also really good nucleophiles, these soft ones.